happy to send that link out to them for viewing at their leisure. But thank you once again for joining all of us. We're very excited to have you here tonight with us. And go ahead and take it away, Trent.
Okay, thank you, Jill. So if you have questions at any point throughout the presentation, just put them in the chat. I know that sometimes we think of questions, we might forget them later. So if they're in the chat, we can get back to them right at the end of the presentation when we have time for questions, and we can make sure we discuss those. So let's get started. My name is Trent Millum, and I am the Water Quality Resources Assistant AmeriCorps member for Green Mountain Conservation Group. I'm joined tonight by my supervisor and the Water Quality Coordinator, Jill Emerson. This presentation will be a joint presentation on our 15-year water quality report and microplastics research update. The 15-year report is a comprehensive water quality report that analyzes the data collected by volunteers as a part of our rivers tributary monitoring program. So in this presentation tonight, I will be presenting on some of our data and results from that project. And then Jill will get to talk a little bit about microplastics as well. The full report for the 15-year water quality report is now available on our website. So if you want to look at the report later, you can download it from there and you'll be able to see everything. There's a lot in there, and so we will only get to talk about a little bit of it tonight. Jill has recently received grant funding from Moose Plate to conduct a study on microplastics in the watershed. So that's going to be, like I said, the second part of our presentation tonight. Thank you to everyone who is here who signed up, especially any of you that have been involved with Green Mountain Conservation Group and our community science research programs. We conduct most of our research and education with volunteers. So if you're ever interested in getting involved, you can learn more about our programs at www.gmcg.org or email or reach out to any of us, and we'd be happy to talk about those. Okay, let's see here. Trying to get this slide to change. There we go. So, who are you hearing from tonight in the presentation? Well, I'm going to let Jill introduce herself first, and then I will talk a little bit more about myself.
Great, thanks, Trent. So for those of you who don't know me, my name is Jill Emerson. I am the Water Quality Coordinator at Green Mountain Conservation Group, and I joined the organization in 2018, and that's a photo, a wildly unflattering photo of me that Trent has chosen to show on the screen. Doing some of our lake sampling. But before I came to Green Mountain, I was at Dartmouth College working in academic research over there in circadian rhythms. But I'm happy to be part of the Green Mountain family. And as Trent mentioned, I'm really excited today to start talking to you about some of the microplastics programming we're piloting this summer.
Great, thank you. And my name is Trent Millum. Like I said before, I'm the Water Quality Resources Assistant this year with Green Mountain Conservation Group as a full-term member. I started last November and will be completing my service term in a little bit less than a month in August. I graduated in 2020 with a Bachelor of Science degree in Earth and Environmental Sciences. And I did a lot of research in college in water quality. I was excited to get my career started in conservation here with GMCG, and I spent a good portion of my fall and winter writing this 15-year water quality report on the Rivers program. So I'm really excited to get to share with you some of our findings tonight. I'm going to have this screen share issue. Okay. So when it comes to our Rivers Tributary Monitoring Program, we are lucky to partner with the Saco River Corridor Commission just across the border in Maine. This project is a joint project, and the SRCC will also have a water quality report that they release soon. So we'll talk a little bit about some of that tonight, but they will have a report coming out with all of their data as well. The SRCC is headed by Dallin Hauser, the executive director, and it is a quasi-state organization founded in 1973. And the Saco River Corridor Commission is committed to protecting public health and safety and the quality of life in Maine, and they also have regulatory capabilities. So GMCG monitors a total of 29 stream sites as a part of the Rivers program, and SRCC monitors an additional 34 in Maine, allowing this to be an entire watershed study. Green Mountain Conservation Group, on the other hand, is a 501c3 nonprofit organization founded in 1997. We are dedicated to protecting and advocating for the natural resources in the Ossipee watershed. And we function using this REAL acronym, or REAL, where the R stands for research, E for education, A for advocacy, and L for land conservation. And we see this as sort of a stepwise process in which we conduct research to understand what we're looking at in the watershed, and that therefore informs our education and our advocacy and how we advocate for natural resources. And one of the ways that we do that is through protecting land and land conservation. We are a watershed organization, and so our focus is on how healthy water is essential to having a healthy community to be a part of. This philosophy drives our drinking water programs, surface and groundwater research, pretty much all of our education, and much more. And finally, what is the Rivers program? Again, the 15-year water quality report is all about data that we have collected from the Rivers program. And Rivers is an acronym, as you can see there. It stands for Regional Interstate Volunteers for the Ecosystems and Rivers of Saco, which I know is a mouthful. But the important parts about that are volunteers, especially. The only reason we have been able to collect 15 plus years of consistent data is because of our amazing volunteers. They're going out every other week from May to October to a stream site and collecting data for us. And that's why we've been able to gather long-term consistent data. We like to use the term community scientists to describe these dedicated volunteers, many of which are here on the program tonight. And then the SRCC also will sample sites each summer from May to September as a part of the Rivers program. And finally, Rivers is a community. If you can see this collage here, it's of our 20 volunteers from this summer in action, sampling at their sites. And we have had countless volunteers be a part of this program since 2002. So these are just a few of them that are involved this year. But again, we wouldn't be able to have any of this data or be able to present any of it without their help and dedication. Rivers did begin in 2002 as a project, but the impetus for the program began back in 2000 when Green Mountain Conservation Group worked with the UNH Cooperative Extension and the Society for the Protection of New Hampshire Forests to produce natural resource inventory maps of each town in the Ossipee watershed. So going out and mapping the important resources, things like the aquifer, surface waters and things like that. And so out of this mapping project came a desire to further look at water quality in the area, which is how the Rivers project was born. At the same time in Maine, the SRCC was working on creating a water quality monitoring program with a desire to better serve the public and also gather long-term water quality data. So it made sense for us to partner with them. One of the reasons it makes a lot of sense is because the tributaries that we monitor at Green Mountain Conservation Group flow into the Ossipee River, the Little Ossipee River, or the Saco River, which is one of the main tributaries or main streams that the SRCC monitors in Maine. So we get to look at water quality throughout the entire watershed by partnering with the SRCC, looking at data all the way from the White Mountains down to the Atlantic Ocean. And speaking of watershed, what is a watershed and why is it important that we talk about a watershed? Well, watersheds are important because everyone lives in a watershed, and water that lands in the boundaries of our watershed, for example, is going to travel into another watershed eventually. And so water quality in our area is very connected to water quality downstream. So the way that we interact with our water here will directly impact others. The Ossipee watershed, which is pictured here in this map, includes 7 main towns: Tamworth, Sandwich, Madison, Ossipee, Effingham, and Freedom, and Eaton as well. And so those are the main watershed towns that we work with. You can see the major bodies of water in this map include the Ossipee Lake system, Silver Lake, and Conway Lake. And the Ossipee watershed is actually just a sub-watershed of the larger Saco River watershed, which is pictured here in this map. The Saco River watershed begins in the White Mountains and flows all the way down to the Atlantic Ocean. And so some of the major bodies of water here are the Ossipee River, the Little Ossipee River, and the Saco River. And although in New Hampshire, where we are, we don't necessarily use a lot of surface water directly for drinking water, that is not the case with the Saco River. Roughly 250,000 people receive their drinking water from the Saco River. And so the way that we interact with our water in the tributaries upstream is going to directly impact the health of the water downstream. And when talking about surface water quality, it is also necessary to look at groundwater. Lying beneath us in the Ossipee watershed is the largest stratified drift aquifer in New Hampshire, which is pictured here in the orange section of this map. About half of New Hampshire's residents receive their drinking water from underground aquifers like this one. And so why do we monitor surface water or care so much about it if we don't necessarily get our drinking water directly from it? Well, water, as you may know in the water cycle, is all connected. And at the same time, our surface waters are very important to us. We care about them. We spend time with our families in them. We recreate in them. We also need them. And then the water that sometimes gets into our surface water will also find its way into our groundwater. And so the health of these two types of water is directly related. So it's really important that we do monitor surface water and do it over a long period of time so we can see the trends that are happening. And so a little bit more about a stratified drift aquifer and why it's important. Stratified drift is a title that refers to the type of sediment and material that we have underneath us where the water is stored. This stratified drift happens to be sorted sand and gravel deposits, sort of like what you would see here in diagram A or C, where the particles happen to be of similar size and they are coarser particles, which means they can store more water. So these are high yielding aquifers that are also highly permeable. There are studies and numbers out there that say the Ossipee aquifer groundwater can travel up to 2,000 square feet a day, which is a lot. And so the takeaway of this is that this aquifer can be easily recharged, meaning that when water falls and infiltrates into the ground, it can easily fill this aquifer up. That also means that if we had, say, a contaminant or pollutant in a particular area, it could also easily infiltrate into an aquifer like this. But we are lucky to have this resource here. It was left by glaciers around 12,000 to 14,000 years ago. And so not a lot of areas will have stratified drift aquifers like the one that we have in the Ossipee aquifer. And so it becomes even more important that we talk about it and protect it. So when it comes to our 15-year water quality report and just the rivers project in general, what were our research objectives and questions when this began? Well, the main one is, what is the quality of water in the Ossipee watershed? Of course, that's what we were trying to look at. At the same time, this is a long-term monitoring program. So we want to see how the quality of the water changes over time and how the landscape impacts it. So essentially, how is water quality changing from one site to another and from one year to another? And this can really only be looked at if we do have a long-term water quality monitoring project. And so that was really the objective. And now that we have 15 plus years of data to look back on, we are able to identify consistent trends and results to report to you. And as this program continues and we continue to gather more data, we can continue to report on trends into the future. So that's really important. And we've mentioned the term water quality a lot, but what really is water quality? It's important to talk about what it really means and how it functions as a scientific discipline. And so it can be defined here as the chemical, physical, and biological characteristics of water, usually in respect to its suitability for a designated use. The designated use is usually set by state or federal regulations in terms of what certain water bodies are designed for, such as recreation or wildlife or drinking water, things like that. And water quality is about measuring certain parameters and comparing those results to standards so we can interpret our results. Those standards are also typically set by state or federal regulations. And again, those standards help us to determine whether a result that we might find is indicative of poor water quality versus good water quality or somewhere in between. If you add in the monitoring part, that's where it becomes a time factor as well. So again, we measure this water quality over time from one year to the next, and that helps us to find important trends. There are certain factors that impact water quality. Many of them are natural, such as geology or the rocks or bedrock material, topography or elevation, meteorology or weather and climate, hydrology or the stream flow and stream shape and size, and also biology, the types of organisms that are interacting with an aquatic ecosystem. Outside of that, there are also a lot of human-induced influences that can cause water quality changes. And so that's where it's important to, again, look at standards if they are set for certain parameters, and to be able to say, is this what we would expect to see in surface water, or could this be a human-caused water quality issue? So how do state and federal standards play a role in water quality monitoring? Well, like I said, we can measure certain parameters against and compare them to standards that are set. In New Hampshire, all surface waters must be classified as either Class A or Class B waters, and then therefore they get certain standards set to whether it's Class A or Class B, what we should expect to see in terms of certain parameters. There are, however, a lot of parameters that don't have a state or federal water quality guideline in terms of what we'd expect to see in surface waters. And so that can make it tricky sometimes to interpret our results. We have to look at other scientific research or other literature that's been published talking about what we would expect to see in water quality and in surface waters. And so we have a few examples of that. If you see this first table here, this comes from our water quality report. And you can see out of our 6 field parameters, these are the ones that volunteers collect on site when they're at the stream. 3 of these don't actually have a New Hampshire quantitative standard set. But New Hampshire does list what we call background minimal disturbance levels, which can be really helpful for interpreting our results. And the second chart here is showing all of our lab sample anions and cations. And again, as you look down the chart, you can see that the federal government, the EPA, doesn't list a recommendation or reference for a lot of these parameters in surface water. So that's where we have to go to bodies of research to help us. Like we have this third column here in the chart that lists typical surface water concentrations we should expect to see out of these parameters. Okay, so for our methods, how do we collect our data and our samples? So volunteers in the program are assigned typically 1 or 2 stream sites, and they go out 1 day a week, every other week, and follow the same rivers protocol each time. This happens bi-weekly from May to October for GMCG at a total of 29 locations. We have a quality assurance project plan, or QAP, that the New Hampshire Department of Environmental Services has signed off on. So all volunteers follow the same exact protocol every time they go out into the field. We do have 10 particular sites in our program out of the 29 that are sampled throughout the winter by Green Mountain Conservation Group staff and AmeriCorps members, as well as some other volunteers. And we collect extra lab samples at these 10 sites. So some of our data is specifically related to those sites. As you can see here in the photo, one of our volunteers, Norm, is taking equipment out into the field. He's got a multimeter and its accompanying probes that are measuring things like dissolved oxygen, temperature, and specific conductance right out in the field. And then they will also collect lab samples that we'll either analyze here in our lab or send to UNH, who does analysis for us with this project. So what is a volunteer sampling for when they get to a site? Well, the first thing that they do is they look at site observations. They take note of what the air temperature is, what the stream appearance looks like. Are there changes at their site that may have caused water quality changes, such as construction or a new dam or something along those lines? And then in terms of the actual parameters, we have water temperature, which is of course really important because temperature impacts a lot of other factors when it comes to water quality. When you have increased temperature in water, it allows more metabolic activity amongst organisms. And so as organisms are doing more, processing more sediment and nutrients and things like that, it's also reducing the dissolved oxygen concentration. So at higher water temperatures, we have lower dissolved oxygen. And at the same time, there are certain fish species like brook trout, for example, that require colder temperatures in water for them to survive, thrive, and breed. And so water temperature becomes a really important parameter for looking at the ecosystem functionality. Turbidity is a measurement of how clear a fluid is. So if you have higher levels of suspended particles or sediments in the water, you also have a higher turbidity. pH is another sample we measure on site, and that is on a scale from 0 to 14, with 7 being neutral, and it's a measurement of how acidic or basic the water is. Most of the natural water in New Hampshire is slightly acidic, and a lot of this is due to the bedrock that we have. In certain areas where there are a lot of limestone, for example, underlying streams, limestone has a better capability of buffering pH changes and keeping it more neutral. Whereas in New Hampshire, we mostly have granite and other metamorphic rocks that cannot do that as well. So we tend to see slightly more acidic waters. And again, that's just a natural factor that's causing that to be the case. but aquatic life typically prefers between 6.5 and 8.2 in terms of pH. Specific conductance is a measurement of how water can pass an electrical current, and this is a really important measurement for us. Water by itself is not a natural conductor, but when there are ions or salts, metals dissolved in water, those can pass an electrical current and increase the specific conductance. This helps us determine how much salt is in our streams because salt is an ion that can pass an electrical current. So as salt concentrations increase, so do the specific conductance. And then finally, dissolved oxygen is one of our most important measurements. It essentially measures the ability of a stream system to support life because every organism needs oxygen to breathe and to survive. Like I said, it is inversely related to temperature, which means that as temperature is increasing, dissolved oxygen concentrations are decreasing, and this is a natural phenomenon. As organisms start to use up more oxygen, or organisms start to use up more oxygen as the temperature increases because they have a greater rate of being able to produce other nutrients and conduct their metabolic activity. So that's just a little introduction into the different parameters that our volunteers are sampling for. If you look at this map, this includes all of the rivers testing sites, both past and present. So we don't currently sample at all of these sites, but you can see them in the yellow triangles on the map. As I talk about some of the data we've collected, I will mention some of our site codes, such as GM1 or OL12U. You don't necessarily have to know what these codes mean, but I'll do my best to point out where these streams are located, which town they're located in, so that you kind of get a context for where these are. And then finally, in terms of how we analyze our data for the 15-year water quality report, we separated it into a field data section, which again is those 6 parameters that volunteers measure on site. And then also a lab data, which is the cation and anion chemical concentrations results that we get from UNH and those extra lab samples. So those are the 2 results section of the report. Analysis was done in Microsoft Excel, RStudio, and ArcGIS for this project and for this report. We also did a man-Kendall statistical analysis, which essentially allows us to get a bunch of data, look at it together, and see whether there was an increasing, a decreasing trend, or there was no trend at all over the course of time. So it's really good at taking a lot of data points and helping us to see overall trends, which is really important for a long-term report like this. So finally, we'll get to look at some of the data now. This first graph, or this first chart, is looking at clustered columns, and this is overall trends amongst the field data parameters. So this is from that man-Kendall statistical analysis. For each parameter, the yellow indicates there was no trend over the course of 15 years, red indicates an increasing trend, and blue a decreasing trend. So the first thing that jumps out right away is the specific conductance bar has red up to 85%, meaning that 85% of our river sites saw a significant increase in specific conductance. In terms of dissolved oxygen, there was mostly no trend and mostly high values in dissolved oxygen. pH, we saw a decreasing trend at around 40% of our sites. And for total phosphorus, we saw an increasing trend at about 40% of our sites. So those are some of the major overall trends that we are seeing, or that we have seen. And these are just some examples of what we will look at in more detail now. So like I said, the 15-year water quality report includes a ton of graphs, a ton of data, and so we only get to see a little bit of it tonight, but these are just a few examples of graphs that you would find in the report in our field data section. Like I said, they're broken up by parameter and by the watershed town that the sites are located in. So the 2 graphs on the left are showing dissolved oxygen in Effingham River's sites. These graphs are demonstrating excellent water quality. The red line is located at 5 milligrams per liter, which is a New Hampshire Class B waters standard. So anything below that would be concerning for water quality. And these are also median values over the course of a year. So this is kind of summing up a year's worth of data and putting it into one data point. And as you can see here, dissolved oxygen concentrations are well above the standard in terms of milligrams per liter, and also mostly for percent saturation on the bottom left. Those are the 2 different ways that we measure dissolved oxygen. If you look in the graph on the top right, It's showing turbidity results for the town of Madison. Turbidity standard in New Hampshire is between 1 and 10 NTU is the unit. Turbidity values across all of our river sites have been really low over the last 15 years. And as you can see here, they rarely even get to around 2 NTU, which is also indicative of very high water quality. And then finally, the pH graph here in the bottom right is for the town of Ossipee. With these particular sites, again, we see high water quality in terms of pH being within that 6 to 8 range. And again, pH was decreasing across 40% of our sites, which is a trend that we want to keep an eye on in the next 5 to 10 years to see if those values might dip below that 6 mark. But overall, these graphs are examples of high water quality. And I will say that across our watershed, we have seen a lot of results such as these. And so you'll find a lot of graphs like these in our report and some text boxes that will interpret for you as well, that these are all results that are showing really good water quality, which is a good sign. Here are some of our results when we look at dissolved oxygen versus temperature and the relationship between the two. If you remember from before, those two parameters have a naturally inverse relationship. As temperature increases, dissolved oxygen decreases. So this is an example of that at 2 of our sites, GF3, which is Cold Brook in Freedom, and GE3, which is the Ossipee River in Effingham. As you can see in the top right graph, when we have a spike in temperature, which is the orange here on the graph, right around 25 degrees Celsius, we have a low point in dissolved oxygen, right around 7 milligrams per liter. And that trend kind of goes up and down throughout the graphs and throughout the years as well. And again, this is just a natural trend that we are able to see in our data. Another way to look at these two parameters together is through the way that we did with the bottom 2 graphs here. These are scatter plots, and it's the same 2 river sites. And so instead of mapping these data over time, we're looking at one data point that has a dissolved oxygen value and a temperature value at the same time. And then we create a trend line, which is the dotted line in the graph. As you can see, the trend line is heading in a downward direction, again, showing that as temperature increases, dissolved oxygen is decreasing. But we also can create an equation from this and get an R-squared value, which is a statistical value that allows us to basically interpret how much of the change in one value is being caused by change in another. So these values are always between 0 and 1, with numbers closer to 1 indicating a very high correlation. So with dissolved oxygen and temperature, we would expect to see a high correlation, which we do see here. It's about 85% or 83% in the graph on the right, showing that these two parameters are very closely tied together. Now, if we take a look at total phosphorus, we again see across these sites especially pretty low values. The red line here in these graphs is located at 26 micrograms per liter, which is a measurement of concentration. And this is the threshold. Anything above this would be considered more than desirable amounts of total phosphorus in a waterway or stream system. And in these particular graphs, you can see that none of the median values are around 26 or get that close to 26, with the exception of maybe a couple sites. The top left is the town of Tamworth and the three river sites that we sampled there. And then we also do have one site in Sandwich here in the top right and one in Eaton in the bottom left. And both of those sites have demonstrated excellent water quality throughout the last 15 years. And then here in the bottom is Freedom. And we measure 6 sites in Freedom, but again, these values are lower than the 26 micrograms per liter threshold. I will point out here in this pie chart at the top of the slide that we did see increasing total phosphorus values at 41% of our river sites. So this is something that we will want to keep an eye on going across the next 5 to 10 years. If these values start to continue to increase and to the point where they are above that red line consistently, then we might have more of a concerning trend for water quality when it comes to total phosphorus. And phosphorus is really a measurement of nutrient overload in stream systems. The fact that we have a very forested watershed helps in terms of not having as many nutrients in the water. And then when we get to specific conductance, this parameter has been one of our main focuses in our rivers analysis. As I mentioned before, it is a measurement of how water conducts an electrical current. you can see in the pie chart again that we saw an increasing value at 85% of our sites. And so the state of New Hampshire doesn't actually list a standard value for specific conductance or a maximum safe limit, but they do indicate a minimal disturbance level at 100 microsiemens per centimeter, which is the unit of concentration for specific conductance. And so we put the red line on this graph at 100. And as you can see, we have two sites in particular in these figures that tend to be on average much higher than 100. That is OL12U, which is Phillips Brook in Effingham, and GO2, which is the Frenchman Brook in Ossipee. And so these median values are well above 100 pretty much every year. And we do have some other values that get to be around 100 in these two towns and with some of our other river sites as well. So this clues us into there being some sort of human impact on the water quality when it comes to specific conductance. And so then we can look further at what might be causing those numbers to increase and to be so high at certain sites. And this is where we get to our lab sample results. So again, like I mentioned, we measure cations and anions at 10 different river sites throughout the whole year. And so this includes values of sodium and chloride, which are two ions that make up salt. And so this is what we know is contributing especially to specific conductance changes. If you look at the graphs here, these are bar charts showing median values throughout the entire rivers program. They are color coded by town as well. And these are the 10 sites that we measure for these different concentrations. There are 4 sites in particular that tend to be much higher than that value of 10. And the reason why we have the red line located at 10 there is because according to scientific research and other literature published, you would expect to see between 1 and 10 milligrams per liter of chloride in a pristine surface water. So anything above 10 might be cluing us in again that there are human impacts. So you see we have GM1 here, which is Banfield Brook in Madison, tends to be much higher than 10. Go back there. Sorry, we're skipping way ahead there. GO2, again, the Frenchman Brook in Ossipee. OL14U, which is Square Brook in Freedom, and then OL12U, which is Phillips Brook in Effingham. So these tend to be our sites that have higher chloride and higher sodium as well, cluing us in that road salt, especially road salt runoff, is getting into our streams and is impacting our water quality. When we start to look at some of these sites in a bit more detail, we can see that some of these chloride and sodium values get to be really, really high. So now we're no longer looking at median or average values, we're looking at instantaneous values. The yellow line in these graphs corresponds to chloride and the purple line is sodium. And again, we have that red line at around 10 milligrams per liter for chloride. You can see that at OL12U Phillips Brook, some of our chloride values get to be as high as 250 milligrams per liter, which is actually the federal maximum safe limit for surface waters. And at GM1 or Banfield Brook in Madison, the values can be as high as 100 as well, which is a lot of salt in our surface water. Another thing that this kind of allows us to look at is sort of how these change over time. So there is also a natural fluctuation in chloride, sodium, and specific conductance over the course of a year. When we have lower water flows, which tend to be in August and September, we usually have higher concentrations of these two parameters and specific conductance. And this is because essentially you have the same amount of salt being dissolved in a lower volume of water. So you end up with a saltier solution in that case. So there is a natural fluctuation throughout the year as well, but you can also see over time at these two sites how the values are increasing. And so how do we look at these 3 parameters, specific conductance, sodium, and chloride, and determine that 1 or 2 of them are impacting the other? Well, we can use these scatter plots again in these correlation graphs like we did with temperature and dissolved oxygen. So the 2 sites here are GO2 in the top left, that's Frenchman Brook in Ossipee, and GM1, which is Banfield Brook in Madison. You can see that as specific conductance is increasing along this x-axis, chloride, which is in blue, is also increasing, and sodium in orange is increasing. And you can see that with the dotted line there on the graphs. And when you look at the R squared values, here in the top left, they're around 90%, and in the bottom, they're around 80%. So basically what we can conclude from that analysis is that between 80 and 90% of the changes that we see in specific conductance are being caused by changes in sodium and chloride. So these have a direct correlation. And when we have salt increases in the streams, we also have specific conductance increases. So what are the impacts of elevated salt levels in streams? This is a big focus in our 15-year water quality report, and it's going to be the topic for most of the rest of my discussion here tonight in the presentation as well, because this is one of the most problematic trends that we are seeing in terms of water quality in the Ossipee watershed through our rivers program. Chloride especially is known to be toxic to aquatic life. It inhibits the growth and reproduction of organisms, reduces food sources for organisms, inhibits their ability to process organic matter in the streams. It can deplete the oxygen. Essentially, it is really harmful for aquatic life and affects ecosystem functionality in general. But it's not just a problem for the stream and the organisms there, it's also a problem for our infrastructure. Salt is very corrosive to roads, bridges, and to our cars as we drive over them. It is estimated that corrosion costs are around $5 billion a year in the United States alone in terms of repairs from salt corrosion. A good example of this impact was the Flint, Michigan water crisis. The Flint River in Michigan is used for drinking water, but it also had elevated levels of salt concentrations due to road salt. And so what was happening is that when people were taking water from the Flint River, it was going through their pipes into their drinking water. It was corroding heavy metals such as lead off of the pipes that were then getting into their drinking water and causing a health crisis. So this can be a big deal, not just for the stream itself, but also for our health and for our infrastructure. And we can see that the salt we spread on our roads is getting into our waterways in increasing amounts. And this is not just an isolated trend for our watershed or even for our state alone. It just so happens that this is a larger trend that has been studied and documented. The National Science Foundation conducted a long-term study looking at salt levels in streams across the United States for over 50 years. And they found that with the exception of some states in the north central part of the country, the New England region and the New England waterways are experiencing the most significant increase in salt levels in streams. And they cite road salting as being the main cause of this. And you can see here on the map, the yellow color indicates there's not much of a trend. Blue indicates decreasing salt levels, and red increasing. So you can really see the New England area here lit up in red. And they also cite outdated salt spreading equipment, overspreading of salt, and salt solutions that are too concentrated when we are using road salt. If you look at this graph here, it just highlights 3 of the major rivers in the New England area. The blue is Merrimack River, green Connecticut River, and red the Blackstone River. And this is only up through 2000, but as you can see, the trend is that salinity or salt levels, concentrations of chloride specifically, are increasing in these major waterways and streams. And so we are seeing this in our watershed and in our tributaries, but we are also seeing this as a larger trend in the New England region as a whole. So in our report, we also detail different ways that we can reduce the impact of road salt contamination into our waterways. One of them is by installing application regulators on our salt spreading vehicles. These are devices that control the amount of salt being spread onto a road by the trucks. Another way to mitigate this impact is by using a salt brining solution. Instead of the traditional road salt solutions, liquid brine is an effective anti-icing agent, and it can be spread more evenly than rock salt as well. It begins to work immediately because the salt is already in solution, and there are studies showing that it can reduce salt purchasing and actual salt usage by up to 70%. So this is definitely one way that we can reduce road salt contamination. We can also just reduce the amount of salt spread in general. We tend to have salt that collects on the side of the roads because there's so much of it, and that can easily get washed into our streams and waterways. As I mentioned, the report said that New England, we had very outdated salt spreading equipment. So that's something that we can look into, is updating that. We can ensure that BMPs, or best management practices, are in place between our roadways and our waterways. And this wouldn't just be helpful for salt contamination in particular, but really for water quality in general. BMPs are really helpful, things like rain gardens or riparian buffers. New Hampshire also offers green snow pro classes, which allows salt applicators to be certified by the New Hampshire Department of Environmental Services for spreading salt in a more sustainable way. So that's an option as well. And then, of course, legislation. We can advocate for and promote local legislation on salt usage in terms of protecting our waterways, and try and start to reverse the trend that we are seeing in terms of our fresh water becoming saltier and saltier. And so what's next for the watershed? Well, the most important next step is to continue long-term monitoring. We need to be able to monitor whether these trends continue or change. We need to be able to continue to evaluate the water quality in the watershed long-term, see if the water quality is decreasing, if it's increasing. We want to be able to continue to report to you guys that the water quality in the watershed overall is very excellent. And so we hope that the continuation of this monitoring program will continue to reveal that to us. We can emphasize coordinated local planning between watershed towns, which is really important. How can we come together and reduce our road salt impact? How can we protect our shared natural resources? This picture on the right hand of the slide is actually a brining machine that the town of Madison has just recently purchased. And this is a really good step in the right direction in terms of reducing road salt in particular. As I mentioned before, we need to continue to promote best management practices on our own properties and beyond. How can we help protect our water quality, and how can we make a difference in that? And then we can also educate and advocate. And that's a constant next step, no matter what. As we continue to learn more about our watershed and about the water quality, we can continue to educate and advocate for natural resources. And then we can also start to put these ideas and thoughts into practice with actual restoration projects, BMP installations, mitigation practices. The thought is great, but the action is also needed to move us forward in terms of some of the areas where we see problematic water quality. So in summary, I want to make sure that it is clear that even though we focused on road salt and salt contamination as one of the major problems with water quality in our watershed, we can safely say from these data over the last 15 years that water quality throughout the Ossipee watershed is excellent and is very high. And there are, like I said, a few trends and emerging threats, road salt being the primary one. Like I said, we saw increases in total phosphorus, decreases in pH, which are important to keep an eye on, and also just increased development in the area, as well as increasing housing purchases, increased number of people moving to New Hampshire. The more we have development and the more people that move here is automatically going to put more pressure on water quality and on natural resources. So that's something that we always need to mention and keep an eye on. If you end up looking at the report more fully, you will see in the appendix section some different numbers about the housing situation in New Hampshire, as well as development and population increase in the area. And so I want to, of course, thank our many dedicated volunteers all the way from 2002 to the present day. Again, we could not have been able to do this project without their help in any way, shape, or form. We also have a big thanks to the Ossipee watershed towns and also our many funding organizations, as well as the New Hampshire Water Resources Research Center at UNH for analyzing a lot of our data and water samples. And then our partner organizations, primarily the Saco River Corridor Commission, Camp Calumet, which allows us to sample on their property and conduct educational programs with them. UNH Cooperative Extension and Lakes Lay Monitoring Program, especially Bob Craycraft, the Town Conservation Commissions, and also Smith College and Dr. Bob Newton, who has been involved in pretty much all of our research programs over the course of many years, assisting us with our data collection and programs. And these are the different references cited just in this presentation. There are many more used in the report. And I think we're going to head over to talk about microplastics at this point. But again, if you have any questions on the water quality report, we'll get to those at the end. And it's on our website, so you can look at it more fully. Wish we could talk a lot more about it, but that's about all the time we have to get into just some of the data that we've seen in the 15 years of that study. So this is on to you, Jill.
Great, thank you, Trent. I know that you spent a lot of time working on this report, and a lot of blood, sweat, and tears went into it. Well, maybe not blood, but sweat and tears anyway went into it. So thank you very much for presenting that to us this evening. As you mentioned, feel free to type in questions into the chat. We will circle back at the end of the program to answer any, or you're welcome to hold them until the end. I'm very excited this evening to bring to you some of our preliminary data on our microplastics project that we started piloting in May this year. It's been it's a wonderful experience, and we cannot thank the New Hampshire State Conservation Committee enough for supporting our project. This is essentially when you purchase a moose plate license plate. This is the funding that the money goes to is to programs like our microplastics program. So thank you to them. And so Trent's going to drag my screen. There we go. So what I'm sure is very unsurprising to all of you is plastic is literally everywhere. And I know that when I initially started thinking about plastic and plastic pollutions, these were kind of the images that I conjured. The one on your far left is, of course, the Great Pacific Garbage Patch, which many of us are aware. We may also think of coastlines in other countries, and including in America, that are riddled with plastic pollution all over the place. And of course, one of the most striking images that I think all of us have seen are sea turtles being caught in plastic pollution, whether it's netting or straws up their noses or entangled in plastic bags. And these are rightfully striking images to show plastic pollution is everywhere. But one of the things that I think people don't understand when I say plastics are everywhere is I literally mean plastics are everywhere. So we, the scientific community, have found plastics all the way at the bottom of Mariana Trench. These are actual images from the bottom there. You can clearly see that that is a single-use plastic bag that has made its way to the deepest part of the ocean. Mount Everest is also riddled with single-use plastics, which is now switching gears entirely, going to the tallest place on our planet, to the point where Nepal in 2020 has now banned single-use plastics to all of their adventurers climbing Mount Everest, because this is what it looks like. But there's also microplastics being found in studies conducted in Antarctica. Recently, 5 times the amount of microplastics that were predicted were actually discovered in Antarctica, which is pretty alarming. And the same thing for the Arctic Circle, of places that are hundreds of miles away from any civilization where you can only chopper in, they are finding plastic pollution there, which is just really incredible when you think about how ubiquitous plastic has really become. Pretty much, if you do any of these 3 things, which is eating, drinking, or breathing, you have had, most likely currently have, and will have plastic pollution in your body. So how, why, how, you would think you would notice if you are consuming plastic, right? That just seems like a thing we would notice. But what's actually happening is that we are consuming microplastics. So the general term for microplastics is that anything that is 5 millimeters or less in length. So if you think about what 5 millimeters is, that's visible to the naked eye, but you're starting to get to the limit of what some of us can see anyway, at least me. And microplastics can also be smaller than that. Once you hit something that's 1 micrometer, which is usually smaller than what our water filters are, you're now into a category called nanoplastics. A lot of times microplastics come from a larger plastic item that has been mechanically degraded somehow, whether intentionally or not, or has been photodegraded from the sun, or maybe from weather conditions have also degraded something. And largely they come in three broad categories. There's of course subcategories to microplastics, but by and large, these are the three categories we deal with. Microbeads are probably the only one that is actually intentionally produced to be small. Microbeads are things that are commonly found in cosmetics or lotions, hair care products, facial scrubs tend to have a lot of microbeads in it. And the good thing is in 2015, the Obama administration banned the use of microbeads in cosmetics starting in 2018. That being said, we are obviously not the only country manufacturing anything. Other countries do not have that, that type of ban. And that also doesn't mean that your cosmetics don't contain plastic. They just may not contain microbeads. The second broad category of microplastics is considered microfibers, which this is pretty much anything that comes from a piece of clothing or a bag or anything that is cloth-like. So polyester tends to be a really popular synthetic that is in clothing. And when you wash those clothes or wear those clothes out into the environment, you are shedding small bits of those clothes over time. And so we can actually go in to different environments and find those microfibers in a variety of colors, like the ones that you see here. The final broad category is microfragments, which is pretty much, it didn't fit into the other two categories of microbeads or microfibers. And these are usually oddly shaped pieces of plastic that are highly likely to have come from a larger something. Maybe it was a tarp or a plastic water bottle or a bucket. Literally the possibilities are endless. So those are kind of the three categories that we're dealing with for microplastics. And so these are the categories that we're trying to look to see what we find in different aquatic systems. So a lot of the studies that have been done on microplastics have been done in marine environments, which absolutely makes sense. Every single one of the gyres tends to have a garbage patch, maybe not as big as the Great Pacific Garbage Patch, but they do tend to have their own little garbage patches that maybe don't get as much attention. And that's great. That's undeniably wonderful that we do have data in marine systems. We also do have a lot of data that has been done from experiments conducted in very controlled laboratory settings where, for example, seeing if plankton would consume plastic of it's a singular type of plastic that is all uniformed in shape and is potentially one kind, which is not really what you would find in the environment. And again, these are undoubtedly useful and necessary experiments, but there's a surprising gap in knowledge about what's happening in freshwater systems. So here on the left, you can just see a quick like visual reference of that from a singular group called Adventure Scientists, which are an organization that is not only conducting their own microplastic research, but is also compiling other people's research who are willing to donate the data to a singular hub. And what you can see here in the green is anything that has been a study done in marine environments, anything in blue has been done in freshwater. And the green by and large outweigh any of the blue freshwater studies. Fortunately, in the last couple of years, more freshwater studies are starting to be done, which is great and definitely necessary to better understand what microplastics are doing. The long and the short of it is we don't really know human-wise what microplastics are doing to us when we consume them, whether accidentally in our surface waters when you have a little kid who maybe sucks down some water while they're swimming, or even in your drinking water. There are some hypotheses that the microplastics might be like a life raft for bacteria to gain entry into a system. They possibly are a life raft for other chemicals to get in. They might be doing absolutely nothing and they just pass on through. We don't really know for health benefits what the effects are. So in order to help fill some of those gaps, we're taking a look at microplastics in the Ossipee Lake system. So the little map here and the little Google map is just, if you're unfamiliar with the Ossipee Lake system, here it is. Ossipee Lake is one of the larger lakes in New Hampshire, and then it does have a series of bays that come off of it. And our survey for this summer is going to be a 3-part survey that we're conducting. The most important and probably time-consuming one is actually water samples. We're both going out to the deep spot of each of the lake, the big lake and the bays. And we're collecting water from the surface down to the thermocline, which is in our area roughly 5 to 8 meters, give or take. We're also collecting surface samples just by taking a giant net that looks very much like a windsock and throwing it behind our boat and then towing it behind us at a very slow rate of speed, which I'm sure is driving other boaters crazy. But then we're collecting samples that way too. Our second part of our survey is we've taken some sediment samples from various spots around the Ossipee Lake system. So we're going to be looking at not only microplastics that are currently in the water, but things that have now come ashore and see how many of those we can find. And then lastly, we're also looking at freshwater plankton in our system to see if we can determine if any of the plankton are consuming the microplastics. Plankton are a really essential part of the food web. Many aquatic systems live and die based on plankton availability. So it's really important for us to study the base of the food web, which would be our plankton. And so off to the side here, you can see some pictures of me and Trent doing some of those collections with our plankton tow, and kind of looks like we're playing in the sand with our sand buckets, but we have to try to be really careful to even minimize the utensils we are using in this survey so that we're not accidentally contaminating our samples with plastic. We do a good job, we're not perfect, but we are constantly thinking about every collection method that we do in this. So in order for us to better look at what plastic we do have, we are utilizing a chemical called Nile Red. And Nile Red is basically a commercial dye that you can buy from any major realtor who deals in chemicals. It was originally used to stain lipids or fat cells, but it's been discovered that it actually adheres to many different types of plastics. Not all types of plastics, but many different types. How it's adhering to that is not widely understood, but the best hypothesis is that Nile Red is nonpolar, plastic is nonpolar, water is polar, and nonpolar things like to hang out with nonpolar things, polar things like to hang out with polar things. So the Nile Red is attracted essentially to this nonpolar plastic bits floating around in the water. Once we've done that stain, we actually are able to shine a blue light onto our plate that we take our water sample and we filter it down onto a filter, and we just stick that filter in a plate so we don't lose it essentially. And we dye that filter, let it dry, and then we shine a blue light onto it and we take a picture through an orange filter. So the blue light excites the Nile Red. We filter out all of the other wavelengths, so only the orange yellowish can come through, and then we're able to actually snap photos. So it's a really cool technology that we're very excited to be bringing not only to Green Mountain, but into this area of New England. So the first things first, when we've got this, we did a lot of playing around with stuff to figure out how it works, for lack of a better term. So we wanted to make sure that our dyeing technique and the way that we were taking pictures was going to be useful and actually as written. After many years of doing academic science, I can tell you, reading somebody else's paper and then trying to recreate what they've done sometimes works great and sometimes doesn't work at all. So nice to know that it actually works. So here we have on the left is what I was calling a spike control of, we ground up a little bit of plastic that were probably at the edge of what a microplastic is and maybe just getting into like out of that 5 millimeter range. But we wanted to be able to visually see it with the naked eye and then see it with the Nile Red. On the right is just the filter with nothing on it. And we dyed them both and treated them the same. And you were able to see in the spike control, all of that bright yellow squiggly stuff is plastics that were picked up by the Nile Red. Now we do see some spots in our blank control. Our membranes do have some autofluorescence to them that we are working to try to clean up a little bit. But by and large, you can definitely see the difference between the two plates of when you have plastic, you get this really brilliant image. And when you don't, you've kind of got a relatively consistent yellow background minus a couple of points here of autofluorescence. So that's great. We're excited. We got it to work. So here's the first look of some of our samples. We haven't been able to process as many of these as quickly as I'd like, but we are working through it. So the first thing that you see is a lot of red and orange. This is, again, the orange filter that you're looking through. This big plate at the top is a 100 milliliter sample of a tow that we did between two of the bays. And one of the things that you might notice from the full plate immediately is there's 4 or 5 specks kind of in the bottom third of the plate that immediately jump out to you. Of those are very bright, vibrant, fluorescing pieces of plastic. When we take a closer look with a microscope that we MacGyvered, for lack of a better term, in order to take some of these pictures on a close-up, you can see that we are generally finding those broad categories of plastic that I mentioned earlier. So on the left here, you can see that there's a couple of microbeads, which are very circular in shape. There is a chance that those are micro fragments, but I'm guessing those are microbeads for how uniformed they look. And here, you know, there's a picture here of a microbead and a microfiber together. In the middle here, you can see some of our better images of microfibers. And you do see that some of these are also in slightly different colors. So you've got some that are like maybe a deeper red and some that are a brighter yellow. That's a little bit to do with how we take the pictures, but there are reports that we should be able to tell not only if it's plastic, but generally the type of plastic. So if it's polystyrene, for example, it'll have a very specific red, green, blue value to it. I haven't gotten that to that point yet, but I'm hopeful with these pictures that I will. But for right now, we're just looking for if it's plastic or not. And then finally, on the right-hand side, you can just see some microfragments, which are kind of all over the place in shape, that there's nothing really defined to them, but they are all very vibrant. And so what we do is our filter paper is gridded. So we count grid by grid how many we find in each sample for our water samples. And so here are some of the preliminary numbers from May and June. I haven't had a chance to process July yet. I'm still working on finishing up June, but you can see here that we are definitely finding plastic in our water samples. Some bays and lakes are seemingly have higher values than others. We're still doing a little bit of troubleshooting, trying to make the counting easier, because right now we're doing manual counting, but you can see that we are definitely picking up plastic, which is not terribly surprising from what we know. We know that there is plastic everywhere in the world, regardless of where you look, of whether it's been there from you know, the water cycle or atmospheric deposition. We're literally finding it anywhere. So this was unsurprising, but a good first step to show that we do see it and that our technology is working. One of the things you may notice in the June sample at the very bottom is the trawl. Can you go? Thank you. The trawl has 423 pieces of plastic in it, which was definitely very different looking at a trawl plate versus looking at the deep water samples. This does make sense though, because we are literally just towing a big net across the surface of a very large stretch of water. And so I'm really curious that we have now an even bigger net that we've purchased of how many microplastics we're going to now collect, hopefully next week, in that much larger net. So going forward, we're going to continue with our monthly sampling. We're working through a lot of the collection techniques that we're working through troubleshooting our collection techniques, but also our counting techniques. We're finishing up our VLAP, which is our lake monitoring series, coming in August. So those will be the last samples we collect for this program. We also have collected some sediment and we are processing it and troubleshooting some of that. And we did do our very first plankton tow, where we took 0.4 grams of dried plankton, which was a fun experience for all who participated in it. And we're able to grind it up and digest it down in an alkaline solution. And we did find 19 pieces of microplastic found in that. I would like to be able to run that again more times, so I have a little more confidence in what I'm seeing. But we do at least have a working protocol for that. So it's very exciting. We've also started on some educational endeavors. So we've taken this program on the road essentially and worked with the Calumet Camp as part of their environmental program to teach kids about microplastics and how to find them. And we're also going to Effingham Summer School next week to do the same type of program. And now we are incorporating a microplastics portion into our annual VBAP program, which many of you know and may have participated in. And we'll continue to give talks on this as data develops. A lot of our first efforts were a lot of troubleshooting and trying something and having it not work and going back and trying it again, which is pretty much science, but we're getting there slowly and surely. And we're very excited by the first images that we've been able to obtain through this grant.
Okay. Thank you, Jill, for sharing about the research that we have started here at Green Mountain Conservation Group with microplastics, and we're excited to get more results on that. Before we close up here, I just wanted to mention some upcoming GMCG events for the end of the summer. We have our big Watershed celebration and Wonders of Water Art exhibition on Thursday, August 12th, from noon to 3 p.m. There's going to be food here. We also have the Wonders of Water Art exhibition. So if you want to submit a piece of art for that, you can do so in the next week or so to be a part of that. But that's going to be a good chance for our volunteers and everyone just to get together and have some food and hang out. On Zoom on August 18th from 7 to 8 p.m., we have an Abenaki Tales from the Northeast Woodlands program. And this is going to involve a Native American Abenaki speaker who will share stories and tales. And it's going to be a really great program. And then a little bit further into the fall, this is now in person on Saturday, October 9th from 2 to 3 p.m. We will be doing a Wild Mushrooms of Fall with Stephanie Doyle of the New Hampshire Mushroom Company here at the Blue Heron House. We'll be giving a mushroom walk. So those are just a few of our upcoming events. But again, if you want to know anything more about Green Mountain Conservation Group, you can always go to our website, www.gmcg.org. So thank you for listening. We really appreciate all of you being here tonight to be a part of this program. And we will now answer any live questions or questions that have been put in the chat. I haven't seen myself questions in the chat because I've been sharing my screen, but if there are some, we can definitely answer them.
Yes, you have some questions, Trent. So we're just going to start from the first one that was received. Looks like your dad wants to know, other than road salt runoff, what might be increasing the level of salt in the water?
That's a really good question. Road salt or salt in waterways can come from other things as well. One of the trends that we saw, or that has been observed in scientific studies out west, is that they were having a lot of salt in their streams, not from the road necessarily, but from irrigation and from agricultural fields and things like that. So any place that it can really collect. It's easy to pinpoint road salt in our area simply because we know that it's spread so much. We know that a lot of it goes down onto the roads and that we have harsher winters and therefore need to put down more salt for de-icing and things like that. So it's kind of easy to pinpoint where it's coming from, but that's a good example of sort of a non-point source pollution where you can't really be 100% sure where exactly something is coming from into a waterway. You can use sort of context clues, land development, land area, what types of like forested land, do you have a lot of roads or waterways, or are you in an area where there's a lot of snow, or is it very agriculture heavy? Those can help us determine where something is coming from. But yeah, agriculture can be another source for salts and irrigation onto agriculture fields especially.
Okay. There is another question that is, how can we help our legislatures recognize the advantage of brining, which is increasingly utilized in the mid-Atlantic states? Yeah,
I think the big key for brining is to start using it and for that to be the sort of the impetus. And it's really awesome that the town of Madison now has a machine that can spread brine. The cost of getting a brining equipment is fairly high, and that tends to maybe be sort of what causes us to be reluctant to transition more to that. But the amount of salt that we're purchasing every year by not using brining is essentially costing more, that if we were to get this kind of equipment within a couple of years, the cost would offset by the 70% reduction in salt that we're actually using. So that's definitely something in terms of speaking about it monetarily. that this will kind of pay off in the future, and it's going to be much better for our road systems and roadways, which will also reduce the costs that might be needed to repair infrastructure. So there are a lot of reasons, and I think the starting point is really to use it and to gather data and to say, okay, we've got brining now. Here's how much we reduced our salt cost this year, or here's how much we reduced our salt usage, and then to then be able to back that up, hopefully with scientific data, and say, okay, we're actually seeing a different trend now in our waterways where they're not becoming more and more salty. That is now declining and decreasing. So a lot of different factors, but as you say, it's becoming more utilized in the mid-Atlantic states and hopefully more in New England as well.
So the next one is a question on cyanobacteria. Is GMCG tracking instances of this and correlating causes? Do you want to take that, or do you want me to take that?
Yeah, I can start there. And if you want to definitely jump in, you can. But cyanobacteria is something that we are sampling more so on a case-by-case basis in terms of the cyanobacteria bloom occurs in one of our nearby water bodies, and we are sort of assisting the state of New Hampshire in being able to go out and collect a sample and identify that. I do think that we would like to, as an organization, probably track this more as more of a research study, an ongoing study in terms of how this can impact water quality, and kind of add it into what we're already doing with surface water quality. I don't know if you want to add anything to that, Jill.
Yeah, so it's difficult to know exactly the correlating cause in respect to, it's phosphorus essentially is the correlating cause. Where that phosphorus is coming from is most likely external loading. But it's these conversations can quickly devolve into a bunch of finger pointing of, well, this place is causing more of the non-source point pollution. Cyanobacteria need three things. Essentially, they need sunlight, phosphorus, and nitrogen. We can't control the sunlight. They'll actually fixate nitrogen from the atmosphere into the water. So if it's there, super, they'll use it. They're lazy. But if it's not there, they'll get it. So phosphorus is really the limiting factor there. So we can see in places like Danforth Bay has a higher level of phosphorus in its hypolimnion, and I don't remember off the top of my head of its two other lake layers, but definitely in its hypolimnion. And that location does have cyanobacteria problems, most likely because it is being fed phosphorus on a somewhat continuous basis. The best way to start to mitigate that is by using those best management practices that Trent mentioned earlier of trying to stop external phosphorus from ending into your system. Yeah, so good question there on that. Hopefully I answered that, but if not, that was, Rich knows where I am.
So I think the next question is probably for you, Jill, in terms of how does such a large quantity of plastic usually find its way into the ocean or freshwater bodies, those being different systems, obviously.
Yeah, so it's, to use a Finding Nemo quote, all things lead to the ocean. There's a lot of just downhill movement from places up high to bodies of water are usually the lowest parts of an area. So it makes sense that they would pool into this one area coming from all over. As I'm sure everybody is well aware of, that we have a general plastics problem of literally, you could look around any single room that you're sitting in and probably find dozens of things that are made of plastic or partially made of plastic. And this has really been an issue since World War II and after, where we became a society that is really heavily codependent on plastic use. And plastics definitely have their time and their place. And I would never argue the elimination of all plastics. But if you think about what we are now using plastics for, the single drinking water bottle that you have, the rope line that you might use for your boat, you cover it in a big tarp at the end of the year. All of our bathing suits are polyester based. It's death by 1,000 paper cuts essentially. So you're getting these aggregates anyway in these low land areas because that's where everything is traveling to. Okay, Spencer has a question for you. In the graph showing the concentrations of sodium and chloride, were you able to deduce, nice word, why the sodium concentration was lower than chloride, other road salts or pre-wetting agents that contain chloride? Oh, sorry, other road salts or pre-wetting agents that contain chloride, like magnesium chloride, calcium chloride, potassium chloride. I might just go ahead and answer that for you. Yes, there's other types of road salt that some organizations or some road agents will use calcium chloride if it's a lot colder outside. So that's why we do look at sodium, but the chloride is really the key because all of the salt components that people will use, whether it's in a road salting agent or just the stuff that you sprinkle on your walkway, will have a chloride component to it.
There's also, at those particular sites where we measure sodium and chloride, we also do have measurements for magnesium, calcium, and potassium.
Right.
Three of the examples used there. And those concentrations were all much, much lower than we see in sodium. I don't know, it's a good point to bring up though, what type of road salt do we know what the towns are using in terms of what actually makes up the salt that they're spreading? As it's probably obviously much more complex than just sodium and chloride. Which is just more the traditional like table salt. But yeah, but we do see higher concentrations of sodium and chloride specifically when compared to the other ions such as magnesium, calcium, and potassium.
So we also have a question. Can this information be shared with industries who manufacture clothing for sports endeavors towards inspiring them to increase their efforts to eliminate polyester, et cetera, in their products? The very short answer to that is yes, of course. Whether or not a change will be made is really hard to say, but we do need to move away from being as codependent on plastics as we are. And this is not quite a thing to your question, but one of the ways that we can do this is by everybody's favorite activity, or it comes and goes in waves, is by thrifting. Having clothing typically sheds the most microplastics it will shed in its first or second wash. It will continue certainly to shed plastics, but at a significantly reduced rate. And since those clothings already exist in the world, we should be using them as much as possible and then recycling them when we can. Honestly, the best thing that we could do for plastics as in general is to force manufacturers, especially big conglomerates, to recycle their plastic. There are so many virgin products that are made every single day that we say we recycle them, but it's only about 4% of the plastic we create annually actually is recyclable. There is no pressure for any major manufacturer to recycle what they have created. It is far cheaper for them to create virgin products. So other countries do have rules and regulations for big conglomerates having to recycle their own plastic, but we in this country do not have that. And that would be a huge step into helping our plastics problem. You can blame the consumer all you want, and there's definitely things each of us as an individual can do, but we're going to need big conglomerate help to actually solve this problem. Tara is promoting the Green Snow Pro trainings, UNHT2. So if any of you know of contractors who do salt laying down or might be interested in this, there's definitely New Hampshire T2 holds classes every year. I think they're in October, but there is a link that she's provided to DES if you or anybody you know is interested. And that looks like all of the questions from people, which we've definitely gone over time. If anybody has any last minute questions, we'll wait a minute or two. But we do thank you for joining us today. Hopefully you guys learned a little bit about both of our rivers program and about microplastics in general. And should you be like me and think of the question at 3 a.m. of like, I wish I had asked that, you are more than welcome to email us at info@gmcg.org, and we will get your message and happily answer any of your questions. So I'm not seeing any new questions, so I think we can. Trent's linking the 15-year water quality report as a quick link, but that is also available on our website for anybody who really wants to take a deep dive into the data we didn't cover tonight, because there is a lot of it. So thank you. Thank you to Trent for lovely presentation. And again, thank you all for joining us, and we hope you have a really wonderful evening.
Thank you.
Thank you so much. I wish more people were here and more people heard this because so much to learn and so much to share, and people roll their eyes when I get started. But thank you all very much.
Keep sharing.
Thanks, guys. I thought that was a great presentation too. The microplastics research is great. I think that you guys could really help to change a lot of people's minds on plastic, especially with the plastic bag ban that recently was implemented in Maine. So, oh yeah, it was a big victory, honestly, and a lot of people don't understand why. So this is a great project, and I think if you really targeted outreach with this, you could probably change the mind. So thank you.
Yeah, we definitely have an outreach component, and we've received, we've taken this, as I mentioned, to a local kids camp, and that actually has been really well received there from the students who've attended, and even the counselors who are there, who, you know, they kind of don't start paying attention, and then their ears perk up, and then by the end of it, they're right alongside the campers learning about the program and how to find microplastics, and it's been really nice, and a really nice educational program to get out to kids that we otherwise wouldn't have been able to reach, because they're summer kids that, you know, hang out in New Hampshire for 2 weeks and then bounce back to wherever they're from.
That's great. That's great, Jill. Yeah. I think that could really be helpful for a lot of other our community members. Really, a lot of people don't understand the damage that plastic does. So
yeah, so by 2050, we're going to have more plastic in the ocean than we do fish.
that's a real problem.
That's a real problem, and I'm going to see that, which is frightening, because I can't even say like, this is some far off thing that I won't live through, which I will see that, and that is just horrifying on so many levels.
Well, it's good that you're working on this project then.
Thank you.
Thank you again.
It's scientifically a lot of fun to figure out the technology. So it's been very rewarding in that case. Trent's probably rolling his eyes because there's been a lot of just jerry rigging and troubleshooting and MacGyvering something, and then MacGyvering your MacGyver, and but I find that very rewarding.
You guys are doing a good job, so we all appreciate it.
Thank you, Dallin. Thanks for tuning in. We appreciate it.
Absolutely. Thank you, guys. Thank you so much. Good night.
Night.
Good night.
Good job.
I don't know if
All
anyone's
right.
hanging around for any particular reason. I could end the meeting if we feel like it's appropriate to end the meeting.
Yeah,
But-
you can stop the record. Oh, I can stop the recording too. Look at that. Do you want to stop?